All right, we are now recording. Let me get PowerPoint up. And we'll go from the current slide. Oh, haven't turned on the projector yet. Thank you. I think I would get my nose if it wasn't set to my face. And let me also get the lights fixed somewhat. Now, do you prefer those lights on or those lights off?
It's fine.
Which?
It's fine. That's
off?
Okay. It's off.
But if it gets too dark, let me know and we can turn the... Some of them, the fewer light bulbs come on with one switch than on the other. These, none of them come on because I got them both off. Okay. Now, my memory and my mark on the page had us getting to the top of page 126, for those who have a book now. And going to introduce a couple of sort of a notation type thing, okay? We mentioned Newton's first law. Do you remember that one? Okay, still not coming up. There we go, finally, okay. Okay, we talked about Newton's first law. Anyone remember it? Basically, an object does not change its state of motion unless it's operated on by an unbalanced force. There's no one down here. I'm going to turn these lights off too. Not that it bothers anything, I just don't like the way it's electricity. Okay. So, an object's state of motion remains constant. If it's at rest, it stays at rest. If it's moving, it keeps moving, unless it's acted on by an unbalanced force. Okay? First law of motion. Second law of motion is, if there is a net force, an unbalanced force, then obviously the state of motion changes, meaning velocity changes, which means a change of velocity is an acceleration. So the body accelerates. It either speeds up, slows down, or changes direction. So we talked about the one formula that's really important in Newton's second law, sort of the foundational formula in Newton's second law is F is equal to ma. Now this force is a net force, not any individual force. The total force is acting on that object. Okay. Mass is what's related with inertia. The inertia of the object is what it is, okay? Acceleration is a change of velocity, change of, it may be speed, but it could also be direction, or both. Okay, now, they introduce a little bit of a new notation here. If your mass is constant, which a lot of problems it will be, it's not going to be changing a lot, then we say that the net force is proportional to the acceleration. And they use this little symbol like that. Other texts will use something like this, meaning is proportional to. Okay? This book uses this one. Not an important issue, but just issue. Now, if the acceleration, if the force is constant, the net force is constant, then we say, and I'll write it the same way they do, that the mass is proportional to 1 over the acceleration. So in the second case, we not have the mass constant, but have the force constant. If the force is constant, then it's some fixed value. It's no longer a variable, and then you can divide both sides by acceleration. So the mass is proportional to acceleration. So what is that telling you? Well, the first, if the mass is constant, if you give it more net force acting on it, you're going to give it a greater acceleration. Okay? Or, if it has a greater acceleration, it must be coming from a greater net force. Okay? On the other hand, if the net force is constant, then if you do increase the acceleration, increase the mass, you decrease the acceleration. And if you decrease the mass, you increase the acceleration, and vice versa. If the net force is constant and your acceleration is increased, without a change of force, that means the mass had to be lessened, okay? So, what we call this in physics and in math, these are proportionalities. This is called a direct proportionality, okay? Something is directly proportional, and this is an inverse proportionality, inversely proportional. Think of it similar to this, okay? If you're driving from here to Tuscaloosa, right? If you're driving at a fixed speed, the time it's going to take you to get there is, okay, I shouldn't have said here to Tuscaloosa. If you're driving east, west, north, south, let's just say any direction, if you're driving on the interstate at a fixed velocity, then the distance you travel is proportional to the time that you travel, right? The longer you drive, the further you go. That's a direct proportionality. However, think of this now. If you're driving, let's say, this time to Tuscaloosa, so the destination is fixed. Sorry about that. The destination is fixed. Okay, your length is fixed. And you're driving from here to Tuscaloosa. Okay, and if you're Auburn fans, I'll say here to Auburn, but that's further away, so it's much easier to get on the interstate and go. Okay, here to Tuscaloosa, and you increase your speed, what happens to the time it takes to get there? Yeah, if you increase the speed, don't worry about acceleration. Just talk about distance, time, and speed. Okay. So you got your distance fixed from here to Tuscaloosa. If you increase your speed, what happens to the time it takes to get there? If you drive faster, you get there sooner. So your time goes down when your speed goes up. If you drive more slowly, then the time goes up. So you see, that's an inverse proportionality. Whereas if you had the speed fixed and you drive a longer time, you're going to go a further distance. So distance and time are directly proportional if the speed is fixed. Okay? So the same thing here. If the mass is fixed in this first example here, then the force, net force, and the acceleration are proportional to each other. The greater net force, the greater your acceleration. Lesser net force, lesser acceleration. However, if you have the force fixed, then it's an inverse relationship between mass and acceleration. An increased mass decreases acceleration, decreased mass increases acceleration. That's the top of page 126. Okay? Now, let's talk about units for a minute. I think we mentioned this before, but here are the SI units for force. Okay? Net force is equal to mass times acceleration. Well, mass is measured in SI units, kilograms. Okay? Acceleration in SI units is meters per second squared. Now, get this down, because this sometimes confuses or messes up people. Acceleration is always distance per time, meters per second squared. If your unit was meters per second, that's a velocity. It's not an acceleration. Your units are your friends. They help you understand what's going on with the problem. So when you multiply a kilogram times a meter per second squared, that gives you a unit that we call the Newton. I think we mentioned this before.
When you multiply
The units, kilograms times meters per second squared, that gives you the unit of Newton. That's a unit of force, kilogram, meter per second squared. We call those the fundamental units. You can't get any simpler than them. But the combination of them gives you what we call a Newton. So get used to going back and forth. If you see a Newton, you have to work with units, change it to kilogram, meters per second squared. Or if your problem comes up kilogram, meters per second squared, and you want to save some writing, then do Newtons. Now, are you sure that's not too dark for you to see well? I can turn on one of the lights. It's okay? All right. So, those are the units. Now, if we're talking U.S. customary units, things get really weird. I already told you the net force is measured in pounds, okay? And I think I hinted to you that acceleration is in feet per second squared. It has to be distance per time, okay? What is the unit of mass in the U.S. customary system? That's the one we use every day. We never talk about mass in the U.S. customary system. It's really bizarre. A fundamental unit of nature, and yet, and you're Hallie, right?
Yeah.
Or is it Haley?
Haley.
Haley, I'm sorry, I misread it. Okay. All right. We're on the page we left off, 126, close to the middle of the page there. Okay? Does anyone know what the U.S. customary unit is for mass? It's something I bet you none of you have ever used in your life. Okay? Anyone know what it is? When I write it down, you'll say, you're joshing. You're kidding. No one would have a unit like this. It is a slug. Ever heard of someone going to the store and say, I'd like 3 slugs of beans, please, or celery? Or people would look at you and say, what are you talking about? But that's the U.S. customary unit for mass. No one ever uses it. It's so unused, it doesn't even have an abbreviation. Notice pound is lb, feet is ft, second is s, newton is n, kilogram is kg, meter is m. All those have abbreviations. Slug, no one uses slug, so they don't even bother to give it an abbreviation. If you ever use it, you have to spell it out. Okay? So don't expect to be using Newton's second law that frequently. The book will give you problems in it, but you'll never use it in real life. Okay? You just don't deal with slugs. They're not the little slimy things that are in your garden eating your plants either. That's a different kind of slug. Okay. But a slug is a pound is a slug foot per second squared. Now, they do mention in the book some other units. And back when I was in college, this was a big deal in physics. They didn't have what they call the SI. I'd never heard that when I was in college. What I heard from the metric system was 2 systems. One was called MKS, and the other was called CGS. And what the MKS system was, meters, kilograms, and seconds. That's exactly what we call SI today. The other, when you're dealing with smaller units and entities, was centimeters, grams, and seconds. The second stays the same. And we used to, it made physics so uninteresting, boring, and complicated to have to always you're going back and forth between MKS and CGS. We don't even mess with CGS anymore. But the book does mention it because he was probably an old guy too who had to learn it. So he does mention it. In the CGS system, centimeters, gram, and seconds, then the unit of force there is called the dyne, D-Y-N-E. And I'm trying to remember if that even has an abbreviation. So a dyne would be 1 gram per centimeter, not gram times centimeter per second squared. Whereas a newton is a kilogram meter per second squared. But don't worry about this. It's not a big issue at all. But if you ever need it, that's what it is. Now, there was a dumb joke that went with this, and this helps me remember it. But I didn't hear it from my older brother. And I'm really jumping to the next chapter here. I'll wait, and if we need to, I'll give you the dumb joke in the next chapter. I won't confuse the issue now. Okay, so don't sweat that one. It's not an SI unit. It is, though, a metric unit, but its use is much less common. The pound, we use that for forces. We don't use a unit for mass in the U.S. customary. So I think we're ready now for our first example. All right, to erase the slide? Okay. All right. Example 1, bottom of page 126. What force, now this time I'm going to write it out. In the future I probably won't. What force is necessary, I'm not going to write all of it, to produce, I'll abbreviate it like crazy, an acceleration, I'm going to abbreviate that too, of 6.00 meters per second squared. Okay? On a mass of 5.00 kilograms. Okay. That's the question. Now, I'm going to do a few things here since this is our first example ever. Okay? I'm going to tell you my approach to solving problems. Okay? And it's pretty standard. I may do it a little differently than the textbook sometimes. But here's what I do. First, I look for the question. And the question here is, what force? So this is the unknown. The symbol for force is capital N. And here we're talking about net force. I always like to put sub N. The book doesn't. We'll do that. To produce an acceleration, well, I know what acceleration, its symbol is A. Now, these are symbols. These are parameters. Okay? They're not units. They're symbols. Okay? And this A is 6.00 meters per second squared. And if you remember, I said acceleration always has a unit of length per time per time. Okay? That fits. Now, time out. Why in the world do they have a 0.00? Why didn't they just write 6? Well, that's indicating the precision of your measurement, the precision of the number. That's not just 6 meters per second squared. That's 6 meters per second squared to the nearest 100th of a meter per second squared. So that's precise to the nearest centimeter. That's what that is. Now, I cannot measure accelerations that precisely, but for the sake of the problem, that's it. Now, you might say, well, what's the big deal? We'll get to that later. Okay? Then you read on in the problem, and it tells you mass. The symbol for mass is M. Now, don't confuse that with the unit M, which is meters. That's a completely different thing. Units always have numbers in front of it. The symbols or the parameters, they just stand alone. And this mass is 5.00 kilograms. And remember, that is a unit for mass in the SI system. This is the unit of acceleration in the SI system. Okay? So, here is the unknown, what we're looking for. There's your given acceleration, and there's the given mass. And again, the mass is not just 5, it's 5.00 kilograms. That's to the nearest 100th of a gram, to the nearest 10 grams, it's precise. Precisely that. Okay? So, what's going to be, what formula do we use to relate force, accelerations, and mass? We had it not long ago, written on the board. Force equal mass times acceleration. Okay? So we plug and chug. This is what we're looking for. Plug in the mass, 5.00 kilograms. Plug in the acceleration, 6.00 meters per second squared. And what does that give us? 5 times 6 is 30. Now, here's how you write your answer. 30.0, not 2 zeros, 0, kilogram meter per second squared. But do you remember what a kilogram meter per second square is? A newton, exactly. So that would be 30.0 newtons. Now, either answer is fine. You can use either unit that you want to. It's just easier to write newton than it is to write kilogram meter per second squared. Okay. Now, when you're multiplying or dividing quantities, the important thing is to keep the number of what we call significant digits the same. Any zero that follows a decimal point is going to be significant. If that was 50, you're not sure whether the zero is significant or not. It may be 50 to the nearest 10 grams, so then 5 would be significant, or to the nearest 1 gram, then it would be 50 would be significant. So if you're on the left side of the decimal place, if the zero is significant, you put a bar over it, and we'll see the book do that later. But when they're to the right of the decimal place, any zero you see there will be significant. Okay? So this has 3 significant digits. That has 3 significant digits. So when you multiply, you get 30, but you need 3 significant digits for your answer, so you put a 0.0 there. Not a 0.00, that would be 4 significant digits. You can't get more precision out of a problem than you put into it. You got precision of 3 digits, so you need 3 digits out. If this had been 5.00 kilograms with 6.0 meters per second squared, then your answer would be 30, and you put a bar over the 0 to make it significant. All right. We've got our core group here again. Okay. And if this is in your way, I can move that. Okay. All right. So here's Brianna. And you do use the whole Brianna, right? Last term I had at least 2, maybe 3 Briannas, but they all use Bree. So no, I don't care. I want to know what you want to be called. What do you like to be called? Okay. Well, let me know what you prefer, and I'll try to do it. All right. But it really confused me because different class I say, Brianna, I look over here. Oh, no, this is this one. She sits over there. Okay, so I'd always be losing my breeze. Okay. And that, you'll see, is the answer they have in the book. Okay? Any questions on that? Okay. Now, I might need to repeat some because you just came in. So if there's anything you have a question about, please ask. Okay. Let's do example 2. Now, this is what I think is the strength of this book. I've been complaining about various things. It's expensive. Its PowerPoint stinks. Its test bank stinks. But it gives plenty of examples. And so we'll do the examples in class. Okay? The second example is what force? Hey, same as before. There's your question. You're looking for a force. Okay? Is necessary to produce an acceleration of 2.00 feet per second squared on a mass of, believe it or not, here it comes, 3.00 slugs. Okay? You'll never use it in real life, but here's a problem with slugs in it. Okay? So, what is the unknown? What are we looking for? The force. Now, I like to call it the net force. The book doesn't do that. Okay, that's the unknown. That's what we're going to be looking for. What are they giving us? Okay, but what is that 2.00? Acceleration. That symbol is A. A is equal to 2.00 feet per second squared. Now, it's not just 2 feet per second squared. That's to the nearest 100th of a foot per second squared. That's your acceleration. Okay? And then what else do they give us? The mass is 3.00 slugs. Okay? When's the last time you've ever ordered anything in slugs? You never do. Okay? And what's your formula? It's going to relate those together. Force equal mass times acceleration. Okay? And what's your mass? Yeah, 3, you're right. 3.00 slugs, a really strange unit. What's your acceleration? 2.00 feet per second squared. And when you multiply those together, what do you get? 6.00 slug, what a strange unit, feet per second squared. But what is a slug foot per second squared? A pound, so 6.00 pounds. Now this time, we keep both zeros. Why? Because you only have one digit on the other side. You need 3 significant digits, okay? And since that's in 3, that's in 3, we give our answer in 3. 6.00 pounds. Now, sometimes I wait till later in the course to do this, but I think while I'm thinking of it, it might be a good idea now. If you are worried about how in the world you're going to keep up with all these different units and relate them to each other, I don't know if you remember this, but on the top of page 124, last time we had that 4.45 newtons was 1 pound. Those are conversions, okay? I don't expect you to memorize those things. So here's a handy-dandy thing to do. Go to the back of your book, and this begins on page 686, okay? On page 686, you'll see Appendix C, and these are tables, not tables on which you're going to serve food or anything, but they give some of the conversions that you use. Inches and feet, feet in a yard, yards in a rod, feet in a mile, all these kind of, there's a bunch of things. Okay, if you need to, turn on the light if it helps you see it better. No, you might want to take several pictures because we're going to turn pages. That first page is weights, U.S. weights and measures. Then we have a conversion table for length. And you know this table converts from centimeters, meters, kilometers, inches, feet, and mile. And this table does it for you. Okay? So you sort of get used to how it works. Okay? The next table on that first page is conversion table for area. Okay? On the next page, you have your conversion table for volumes. The table 5 is conversion table for mass. When you're using slugs, grams, kilograms, ounces, pounds, tons. Hey, that's wrong. Ounces, pounds, and tons are actually measuring forces, but we use them as if they're masses. Okay? So you can still do that. Conversion table for density. That's on the bottom of page 687. Flip the page. Conversion table for time. When you're going from years, days, hours, minutes, seconds. We know most of those. Conversion tables for speed. When you're going back and forth between U.S. customary and metric, whether it's SI or not. Conversion table for forces. There's the one, and there you see 1 pound equal 4.45 newtons. So you see, you don't have to find in the book, oh, I know we had that back there somewhere. Go to the table and you'll find it there. Okay, and you can go back and forth any way that you want to. Newtons, pounds, and ounces. Newton is SI unit, pounds and ounces are U.S. customary. Conversion table for power, we aren't there yet. We'll do that in a later chapter. For pressure, we'll do that in a later chapter. Mass and weight density, we'll do that in a later chapter. Specific gravity, we're not going to do that at all. Energy, work, and heat, yes, we'll use that in a later chapter. Heat constants, we won't need those. We won't need coefficient of linear, volume, expansion, and we will maybe use charge. Yeah, in a later chapter we'll use charge. So you see, those are very convenient tables. What I do, I get a piece of paper and mark those so I can know exactly where they are. I can turn to them anytime you need them. You're not going to need them much. Most of these will be in the regular units, but that's where it is, all fixed in a series of tables within pages of each other, so you don't have to flip all over the book saying, I know there was something back there somewhere. Just turn to the back of the book, the Appendix C. Okay? So that was example 2. Let's do example 3. Example 3 introduces a new little wrinkle. Okay? It says find the acceleration by a force. I put capital, they didn't. A force of 500 newtons. And if you'll notice there, they put a bar over the second zero. What does that mean? Remember I was saying, before a decimal point, you don't know what zeros might be significant. If you don't see a bar, you assume none of them are. But if you see a bar, that means that has how many significant digits? 3. The 5, of course, is significant. And the last zero you know is significant. So anything in between that is going to be significant. So that's at 3 significant digits. Okay? If the bar was over the first zero, that would only be 2 significant digits. If there was no bar at all, you assume only 1 significant digit. Okay? So, applied to a mass of 20.0 kilograms. Okay, I hope you can read that. How many significant digits is that? 20.0. That's a 0 at the end, sorry. It's ugly. 20 point. It's 3 significant digits. The 2, of course, is significant, and any 0 after a decimal place is going to be significant. So that's got everything in between. That would be 3 significant digits there. All right. So what are we looking for this time? Where's your question? Not in the form of a question, but what is unknown? The acceleration. That's your unknown. Okay? What do we know? The force, the net force, we assume, is 500 newtons. Okay? Now, I'm going to go on and do this now because I'm thinking of it. Otherwise, I'd have to think of it later. I don't want to think of it twice. So that's the same as 500. Now, the only reason I'm doing this is because I'll need to know the fundamental units. What are the fundamental units that is a newton? Anyone remember? Fundamental units of a newton. Kilogram, meter per second squared. So anytime I need to, I want to be able to go back and forth between those. So there's your net force. Okay? And then what else do they tell us? The mass, which is M, is equal to 20.0 kilograms. I think you'll see why I did the units like that. Now, what formula or equation relates those 3 quantities together? Nothing new here. Force is equal, net force is equal to mass times acceleration. But in this case, we're looking for acceleration. The other 2 times it was net force. So I'm going to give you 2 ways to help remember this. One, since we're looking for the acceleration, let's solve this formula for acceleration. Well, how do we do that? We divide both sides by the mass. Okay? The masses go out here, and you have acceleration is equal to net force, put a little n, divided by mass. Okay? And that becomes our new formula. Now, another little time out here. I was in the U.S. Navy. Okay? I'd already been to college. I knew basically these formulas and stuff like this, but I had to go to some Navy schools. And there's nothing really special about Navy schools. They're just like any schools. But the guys in the Navy school always looking for little tricks and little handles, things to help them remember things. And here's what they used a lot in the Navy. And I've heard other people use them too. It's either called the circle or the triangle. Okay? Now notice what I've done in either the circle or the triangle. I've put a horizontal line. That's going to be a dividing line. Okay? And then I put a vertical line and I'll put an X on it because that's a multiplication line. And anytime you have a relationship, like we do here, F is equal to MA, since the thing by itself and the other thing multiplied, put the F up here and put the M and the A down here. Okay? Now here's the trick. If you're looking for force like we did in our first two problems, that's mass times acceleration. But in this problem, we're looking for acceleration, so cover that, and what do we have? Force divided by mass, and that's exactly what we got there. So if you don't want to remember dividing the symbols around, you can just remember this. This always works when you have something equal to the product of another thing, or something equal to the quotient of another thing. Just put the thing on top of the quotient here, bottom here, and the thing you're looking for there, and then you can solve any one. Mass is equal force divided by acceleration. Yeah? And if you like triangles or circles, whatever you like, they work the same. So, if you want to use those, you certainly can. But we'll see lots and lots and lots of applications that you can use those. Or you can remember how to do your units. It really doesn't matter. Okay? So, just wanted to do that to illustrate, because some people love those things. I've had some students who just, that's what they do. In fact, I can remember when we were having tests in the Navy, I would see people do this. As soon as they got the test, they put their little triangle and circle there. If it's Ohm's law, if it's this kind of thing, whatever it's dealing with, they put their little triangle or circle there so they can always have the formulas right when they need them. They don't have to really remember them. So whatever you think. So here we've solved for the acceleration because that's what we're looking for. Now in reality, you didn't have to do that. This is called, I call chug and plug. Solve for the thing you're looking for and then plug in the numbers. But you could have plugged in the numbers here, like force, net force is equal to mass times acceleration, and just plug in the numbers. This was 500 newtons, or since I wrote it, let me go back and change that to kilogram meter per second squared is equal to 20.0 kilograms times acceleration. This I call plug and chug. Is that right? Yeah. Plug them in first and then solve for A. Well, how do you solve for A? You divide both sides by 20. So whether you want to use 20 kilograms, keep your units, okay? 500, oops. You're dividing both sides by A. I mean by M, which is your 20.0 kilograms. Or this way, you just go straight to this and say A is equal to 500 kilogram meter per second squared, okay, divided by M, which is 20.0 meters. Now, kilograms, goodness gracious. Okay, now, you see the plug and chug, which I typically like to do first, it's more writing to it. If you chug and plug, if you set up the equation first and then plug in the numbers, it's a little less writing. So it's just how lazy you feel or what you feel better about. But either way, you wind up with the same formula. So let's do the math. Now, if you can do that in your head, fine. Otherwise, calculators are perfectly fine. Okay? So if you got a calculator, you want to use it, that's fine. Or if you can do this in your head, that's fine too. They're the same numbers. These go away, and that gives you... Is what?
25.
25. What? Okay. Okay. Now, you had three significant digits, three there, put the 25.0. Now, here's the importance of using your units. Units are your friends. Hang on to them. Keep them. See here, the kilograms will cancel out, and that leaves you with meters per second squared, which is a fantastic unit for acceleration. If your units don't match what you're doing, you've got something wrong. Okay? Units are your friends. Keep up with them. Use them. That's why, you see, I changed from newtons to kilogram meters per second squared so I could cancel out my kilograms. and give me my units at the end. Okay? So anytime you need to, do that. If you don't need to, you don't have to do it. Okay? But you see how we got that. And you have to have three significant digits in your answers that put the .0 in it. Okay. And what did they get in the book? 25.0 meters per second squared. Okay. Notice we use a conversion factor to obtain the acceleration units. I did it right up here at the beginning. It said, what is a Newton? Kilogram meter per second squared. All right. I didn't check my other answers, but I think we got them right. 6.00 pounds and 30. I checked that. We have finished 6.2. And you'll notice here are some problems. Okay? Now, in the book, they have answers to the odd numbers in the back. So here are the ones I suggest you do. You don't have to do them all, but I'd say do some of the odds 1 through 7. Okay? You can get pictures of them if you want to. You're certainly welcome to look at mine. I would do some of the odds 9 through 15. Okay? Now, if you need to turn on a light and get your pictures better, you can do that. Okay? Some of the odds, 1 or 2, all of them, whatever, 9 through 15. And then do some of the odds 17 through 33. Okay? Here's the first, do some of the odds there. If you need to turn on the light, you can. And then some of these and some of those.
You said 17 through?
Through 33. See, there's a whole bunch of them there. You don't have to do them all, but do some representative problems. Make sure you get really comfortable with them. Say, yeah, I got this, and then move on to something else. Okay? Now, I hate to do it, but I'm going to. All right, to clear this slide? Okay. What I'm going to do is go back and see where my other one picks up. Oh, here it is. Not yet. Boo hiss. All right. So we'll go back to this one. All right. And go from current slide. Okay. Now, it seems like a sort of a weird place to put this, but it really is about as good as any. This is talking about gravity and weight. Okay? What gravity is, and we're really sloppy in our language, by the way. When we say gravity, we just do gravity. Well, actually what gravity is a force. That's the force due to gravity. But what we call gravity is quite often just the acceleration that comes from that force due to gravity. In fact, that's what we call little g. Everybody calls that gravity. Well, that little g is the acceleration due to gravity. Okay? So, the weight of an object is a force. Weight, let me get, because this is why I regretted doing that. Okay. Weight is a force. Now, it's probably not your net force. It could be, if that's the only force acting on the object, it could be your net force as well. The odds are that's not the only force acting on it. But it could be in some circumstances. But it's just one of the various forces you could have. In fact, I think, if I'm not mistaken, did I give the illustration of the plane flying at 500 miles per hour? Yeah, and I blew on the paper. The reason I did that, gravity is pulling down on the plane, big time, but the Bernoulli's force is what's lifting it up. Okay, remember we did that. I didn't mention, I don't think, because I think we're right at the end of the class, those jet engines are pushing the plane ahead at 500 miles per hour, but they're hitting a lot of wind resistance. At 500 miles per hour, that's quite a bit of wind resistance, so you have a force acting against you. Now, if that's a constant speed, which is what I said it was, meaning it's not accelerating, the net force on that plane is 0. Gravity is still acting on the plane, but Bernoulli's force is counteracting that. The jet engines are pushing it forward, but the air resistance is holding it back. So the net force is 0 if it's at a constant level of flight, constant speed. Net force has to be 0 because it's not accelerating. Okay. I didn't quite finish my illustration before because I got carried away with Bernoulli's principle. Okay? Now, so what I'm getting at here, weight is usually a component force, usually not the net force. But its formula follows something very, very close to what we have. Now, what they call weight is F sub W. Now, in some other books, that's usually written F sub G. And if I write F sub G, don't get too bent out of shape. Just say, hey, this book calls it F sub W. Because most of the other physics and physical science books I'm teaching from now call it F sub G. But F sub W is what this calls it. And F sub W is equal to the mass of the object times the acceleration due to gravity. We call that gravity. Everybody says G is gravity. No, it's the acceleration due to gravity. And you see that form is just like net force is equal mass times acceleration. That's a net force, and that's the acceleration of the body. This is the specific acceleration due to gravity. Okay. Now, is that true everywhere on the surface of the Earth? Pretty much. That acceleration due to gravity is constant on the surface of the Earth. But you know what? When those astronauts go up into space, what do you see them doing? Floating around as if they're weightless. Well, they're not really weightless, but they're pretty close to it because the acceleration due to gravity up there is very, very low. Okay? If you're on the moon, if you ever watched those videos of the astronauts when they got to the moon, even though they're in the big, heavy, bulky spacesuits, they bop around like they were kids, you know, even though they weigh a ton, but because the acceleration due to gravity is so much less on the moon than it is on Earth. But anywhere on the surface of the Earth, it's going to be a constant. Anywhere on the surface of the moon, it'll be a constant. It'll just be a different constant, much less. If you were on have a problem here because all the other planets that have surfaces are lighter than the Earth, so they're less. I wanted to say Jupiter, but Jupiter doesn't have a surface. It's a gas planet. So if you were on the surface of Jupiter, you'd be falling through, you know, gases. There's no solid surface on Jupiter until you get way on the interior. But if Jupiter had a solid surface and you were on it, boy, the acceleration due to gravity of Jupiter would be huge. Sun's the same thing. Sun is not just gases, it's plasma. And you would be in serious shape if you were on the surface of the sun. You couldn't because it doesn't have a surface. So this is the formula for weight. F sub W, that stands for weight. The force due to weight is mass times the acceleration due to gravity. Okay? Now, in the SI units, the acceleration due to gravity is 9.80 meters per second squared. Now, as soon as I write that down, you know that's an acceleration, don't you? Because it's a length per time per time. That's always an acceleration. 9.80 meters per second squared. That's the acceleration due to gravity anywhere on the surface of the Earth. Whether you're on the top of Mount Everest, which I don't ever plan to be, or in the bottom of the Dead Sea Valley, which I don't, well, I'd like to go there, okay? But it's always very close to the constant 9.80 meters per second squared. But if you're in the U.S. customary system, then that acceleration due to gravity is 32.2 feet per second squared. Now, in some books, you'll see them use 9.8 and 32. when they only got 2 digits of significance. When you use these, you get 3 digits of significance. Okay? That's a constant. Okay? F equal ma, that's a variable there. Whatever your acceleration is due to that force. Here, this is a weight, and that's based on the acceleration due to gravity. Okay. So, example 1 in this section is, by the way, I forgot to get my, and I think we ran into this last time. If you don't tell me, I'll just keep on talking forever. So, y'all keep up with me and don't let me, I know we got plenty of time now. Well, 30 minutes. I thought we had a lot longer than that. See, I just keep on talking. I just love this stuff, okay? All right. So find the weight. I'm going to abbreviate as WT of 5.00 kilograms. Okay? What are we looking for? Where's your question here? What are we looking for? The weight. Okay, and what symbol do we use for weight? F sub W. Very good. Now, a lot of books will just use W. This book uses F sub W. I kind of like that because it reminds you it is a force. Okay? Okay, so that's what we're looking for. What are they given? What are they given? 9.80. Okay, you know that, whether it was given or not. The acceleration due to gravity is 9.80 meters per second squared. Aren't you glad I left that up there? Okay. What else are you given in this problem? Okay, you don't need that in this problem because you're dealing with SI units. So determine what units. Okay. You're given 5. What in the world is 5 kilograms? What do we measure with kilograms? That's your mass. Excellent, excellent, excellent. Okay. Now, what formula relates? Weight, mass, and acceleration due to gravity, which you were very wise to say you need that. There it is, right up there. F sub W is equal to mg. Now, if you want to write that in a triangle or circle, you put F on top and mg on the bottom. Okay? You got it. Okay? And now you plug and chug. So your mass is 5.00 kilograms. And your acceleration due to gravity is 9.80 meters per second squared. And that gives you what? You might need your calculator or not. Anyone know? Anyone got it? 5 times 9.8. 49.0, because you got 3 significants there, 3 significant digits there. 49.0, what units? You could write kilogram, meter per second squared, but what is a kilogram meter per second squared? A Newton, perfect, 49.0 newtons. Either answer is perfectly fine, okay? How'd the book do? Very good, they got it too. Excellent for them, okay? Make sense? Okay. Can I erase? Okay. Example 2. Find the weight of 12 slugs. Okay. Well, you get these 12 little slimy things. No, we're not doing that. Okay. Find the weight okay. What are we looking for? Weight, and what symbol do we use for that? F sub W. Okay, that's the unknown. We don't know what that is. Okay, what are we given? And what is that a measure of? Slugs measure is not weight. Mass. That's the mass measure. We never use it in the U.S. customary, but it is. That's U.S. customary for mass. Mass is equal to 12.0 slugs. There's no abbreviation for it. You have to spell out that ugly, nasty little word. Okay? Now, what don't we know here, or what is left out, but they're assumed that we know? No, we're looking for that. The what? Acceleration due to gravity, which is G. And what is that in the U.S. customary system? 32.2 feet per second squared. That makes an acceleration. It's a distance per time. Okay? So now we can plug and chug, right? Weight is equal to mass times acceleration due to gravity. In this case, that's going to be 12.0 slugs, not that we ever use those, times 32.2 feet per second squared. Okay? I will need a calculator on this one, so someone punch it in for me and see what we get. It's going to be something on the order of about 400 maybe, close to it, not quite 400. Second? 386.4 what units? Slug feet per second squared. But there is a simpler unit than that. What is it? What is a slug foot per second squared? When I got on the scale yesterday, Monday morning, pounds, those are pounds, okay? But what else is wrong with this picture? Your calculator doesn't keep up with significant digits. You have to keep up with significant digits. Okay? How many do we have up there? 3 and 3. Yet you've given me an answer with 4. So what do we do? If you only have 3, you count over 1, 2, 3, look to the right. If that number is 5 or more, you round this one up 1. If it's 4 or less, you just drop it. So that would be 386. Okay? So this is approximately 386 pounds. Okay? Now, is that super important? Not really, but your book is really big on it. So if you're doing this, checking your answers in the back, if all you have are off by a few digits or something, that's just because they've rounded, and they will always round. I think they always round anyway. So we got 386 pounds. Very good. Make sense? All right. All right. Now finally, we get to the next slide. Wait, I'm hitting the wrong thing. Whoops. Okay. Here, finally, we hit our second slide, okay? And we'll go from this current slide. All right. Maybe it's the third slide, I don't remember. Now, here we have, I'm going to assume this is a brick. Yes. This is a brick sitting on a table. Okay? Sitting on the table. Just sitting there. Okay? Sort of like my computer, sitting on the table. What's the acceleration of that computer or of that brick? 0. It's not moving. So it can't be accelerating, can it? Okay, if it's not moving, does that mean there's no forces acting on the brick? That means there's no net force on the brick. But we know, since this brick is on a table on the earth, surface of the earth, there is a weight. That brick has a weight. Pick it up and you'll see that brick has heavy. So it has a weight, so there is force due to gravity pulling downward. That's our weight. Because the net force is 0, because there's no acceleration, there must be some other force operating on the brick. And that force is the normal force of the table on the brick. The table is pushing up on the brick with an equal force to the weight of the brick, and that's why the net force is 0, because the brick's not moving. It's not accelerating. Okay. Now, you might say, I don't think that table's pushing up on the computer. It can't be. Well, I want you to imagine this, okay? Let's imagine that I were to get y'all know lumber at all? Say a 1 by 12 piece of wood, maybe about 8-10 feet long, and I put it between this table and that table, okay? A 1 by 12 piece of wood. And then y'all are going to help me climb up some steps here, and I'm going to step on that board. What do you think that board's going to do? Second?
It's going to break.
Boy, she thinks I'm really heavy. Okay, thank you very much. No. Okay, it will probably break. But at first, it's going to sag like crazy because the board is trying to hold me up. But it probably doesn't have enough of a normal force to keep me up, so more than likely it will break. Now, if I do a 2 by 12, it may sag a little, but I think most of the time that would hold. But 1 by 12 probably wouldn't. So it probably would break because the 1 by 12 wouldn't have enough normal force to counteract my weight. So it would probably break. It certainly would bend like crazy. The 2 by 4 probably would bend a little bit, but that tension would be enough to hold me up. So sure enough, this table is pushing up on this computer with an equal force to its weight. Here's the other way you can tell that. Stick your finger under there and you can feel that now your finger is pushing up with that weight because it's pushing up on the computer. Okay? So there's always a normal force. Okay. Now, this is an example of Newton's third law. The book is not going to go into it now. I think they wait and do it later, and I don't know why. No, they don't. Yes, they do. They wait till the very end of the chapter, but this is an example of Newton's third law. Anytime one object is exerting a force on another object, the other object exerts the same force on the one. But we'll wait and save that for the end of the chapter. Don't think we'll get there tonight, but we'll come close. Okay? Now, that's what we mean by normal force, the perpendicular force on the contact surface. Okay? Now, that's going to be the next page, but it's a ways off. So I'm going to get out of this and go back to this. Okay? Now, mass versus weight. Now, I pointed this out when we were doing the table back there. We use mass and weight like they're interchangeable. Like you go to the store and you put some potatoes, say, on the scale. And usually that scale has two measures on it. On the outer part, it's in pounds, and the inner part, it's in what? Have you ever noticed? Kilograms. You're absolutely right. Well, guess what? Pounds measures force. Kilograms measures mass. We use them as if they're interchangeable. They're really not. They're only interchangeable when you're on a fixed gravitational field, like we are on the surface of the Earth. And since we always stay on the surface of the Earth, we can use them interchangeably. Because the difference between mass and weight is a constant acceleration due to gravity. So you can just scale it up, okay, or down, okay. Now, if you're moving from here to the moon, no. Your mass stays your mass. Your weight changes. You're much heavier on the Earth than you're on the moon. So what's a good weight loss plan? Go into outer space. You're guaranteed to lose weight. Of course, when you come back, you weigh the same thing as you did when you left, but your weight is less. Your mass stays the same. Okay?
Can I ask you a question?
Surely.
Why do they say, okay, when you lose weight, the inches you lose use more inches than you do weight. What is
Well, that
normal rate?
depends a little bit. For instance, during the break between spring and summer terms, I went to the farm. We have my parents had a farm in Georgia. They both have died, and they left it to the 4 kids, so I have a portion of it, and the others do. So we went over there and did a whole lot of work on the land there because I don't get to go over there very frequently. And I worked like crazy, okay? And I sweated and grunted, and I was sore and all this kind of stuff. I thought for sure when I came back I had lost weight. Well, what I had lost probably some inches, but I had built up muscles, and muscles have a greater density than fat, okay? So therefore I could lose inches and not in fact I gained weight. I ate too much while I was over there, but I lost maybe a few inches. The clothes felt a little tight. Since then, I may be losing weight now, but it's coming back as fat. I'm losing the muscle. So that's why there's a difference there. It really has nothing to do with the physics of it. That's the physiology of it. And believe it or not, even though I look pretty pudgy and stuff, I'm fairly dense. My bones are really, really dense. So I'm a sinker when I'm in the water. Or I used to be. Maybe not. I'm not anymore. But people who are really muscular, which I'm not, quite often they sink when they're in the water rather than float like most of the rest of us do. Now, women have a lower density than men, so y'all usually float. It's usually the men who are the sinkers because we're really dense. Just ask my wife, she'll tell you how dense I am. Okay, but I don't know if that answered your question. Did it sort of? Okay, so mass versus weight, we use them like they're interchangeably, but in physics we have to always keep up. Kilograms are measuring mass, and slugs are too, but we never use those. Pounds and newtons measure weight, or forces, because weights are forces. Okay. So, note that the mass of an object remains the same, but its weight varies according to the gravitational pull. And that's what I was talking about. If you go, an astronaut going into outer space, his weight's going to decrease while his mass remains the same. Mass is the constant of nature. Weight varies by the acceleration. Okay? So on the surface of the Earth, an astronaut who has a mass, let me get my pen back. Okay? An astronaut that has a mass, let me just do it this way. The mass of the astronaut is 75 kilograms. And I don't think very well in terms of kilograms. I don't think that's very massive, okay? Much less massive than I am, I'll put it that way. What would be his weight here on Earth? What's the formula? F sub W is equal to the mass times the acceleration due to gravity. So that would be 75.0 kilograms times what? We're dealing with the what? Well, what? Kilograms is SI. So yeah, you do SI. You look at the other units to answer that question. So that would be 9.80. What units? Meters per second squared. Okay. And then pull out your handy dandy calculator and see what that gives you. 735. That's the right number of significant digits, 2, 3. What unit? That would be a Newton, exactly. So that would be the weight of the astronaut here on Earth. Okay? However, if the astronaut went to the moon, we haven't sent any there lately, but if it would have, the acceleration due to gravity on the moon is about 1/6 of what it is on Earth. So you would divide that by 6, and that would be just 100 and some odd newtons now. that same astronaut, same mass of the astronaut, would only weigh 100 and some odd newtons on the moon. Oh, what a weight loss plan, yes. But as soon as you come back to Earth, as long as the mass stayed the same, back at 735 newtons. Oh, that is the next question. Find the mass of the 75.0 kilogram astronaut when the astronaut's on the moon. And on the moon, this is G on the Earth. G on the moon is 1.63 meters per second squared. So what would be the weight of the astronaut, same mass on the moon? So the weight on the moon, I'm going to put weight on moon, is same mass, 75.0 kilograms. But this time we multiply not by 9.8, but by the acceleration due to gravity of the moon, which is 1.63 meters per second squared. And what would that be? 122.25, is that what you said?
Yeah.
122. Okay, you're right. So I'm just going to wipe out the 0.25, and that would be what units? Second? A little louder? Newton. Okay, perfect. Okay, my hearing's bad, so yeah, because the 0.25 is less than 0.5, we'll just drop it, and that would be newtons. All right, good deal. 122 newtons. Yep, that's what they got to. Note that the astronaut's mass is still his mass. He or she hasn't lost any mass at all, but the weight went down significantly because they're on a different, gravitational field. Okay, now, this one gets a little confusing to me. How are we doing on time? We got a few more minutes. Mass versus volume. It says, do not confuse mass and volume. Frankly, I don't see how you could. But I guess it may be possible. Volume is measured in usually cubic units. So volume is usually a capital V. Now there's a reason for that, because we use little v to be velocity. These are the parameters or the symbols. Capital V is volume. Now, usually if we were talking the volume of this room, what we would do is measure the length of the room, measure the width of the room, and measure the height of the room. So that would be in meters times meters times meters. That would be cubic meters. Or we could measure in feet times feet times feet. That would be cubic feet. Or we could measure in yards times yards times yards, and that would be cubic yards. We could, if we wanted to be really ridiculous, inches by inches by inches. That'd be a huge number. That would be cubic inches or centimeters or whatever. Okay? But volume is usually measured in a cubic length unit. So I'm just going to put L standing for whatever length unit you have cubed. Okay? But there are a few things, and you probably are pretty familiar with them. For instance, can I borrow your bottle right there? Brianna? Okay. Notice it says here, I'm not going to touch anything here at the top. It says here 20 fluid ounces, or 1 pint and 4 fluid ounces, or 591 milliliters. Those are all volume measurements, but you have one too. Those are capacities, which are also volumes. And remember, back of the book in those tables, you'll have the liters, quarts, gallons, cubic meters, cubic inches, all those things, they have units to convert them, okay? And that has nothing to do with mass, okay? So don't confuse those two. Now that, folks, finishes 5.3. Okay, homework exercises here. Do either 1 or 3, or both if you choose, and any of the odds 5 through 9. Okay, because the odds have the answers in the book. and then do sum of the odds between 11 and 29. I'll let you choose which ones you want to do. Okay?
So what was that again, the odds?
Either 1 or 3 or both. Any of the odds 5 through 9, and then any of the odds 11 through 29. Oh, you got the book. Okay. Anyone need the book? Okay. Yeah. You want me to turn on what? That make it easier to take a picture. I thought y'all wanted to take my picture. No, I'm just kidding. Nobody wants to do that. All right, how are we doing? Do we have enough time to get into 5.4? I don't think so. Okay. So,
Time for you to explain.
yeah. All right. So, what we'll do then, we'll start next time at 5.4. Any questions on what we've done so far? All right, good deal. And this time I still was a little late getting here. Well, part of it was some traffic issues too. But I'm still going to shoot for trying to get here at 5. But don't worry, everything's going to be recorded. So if you can't do it, that's fine. All right, then I'll shut down the computer. And by the way, if you have any problems with doing the problems, if you can't get the answers in the back, then please bring those questions to class and we'll work on those.
I'll call y'all this weekend. I'm coming home. I work this weekend. I do too. What time y'all get off?